welcome to this lecture on NPTEL. We will today discuss a new concept, the analysis of antennas by generalized currents. So, actually I recall all of you have heard of Huygens principle. Actually in optics, Huygens gave this principle. Actually this is true for electromagnetics also. I just state the principle. Huygens principle is each point on a primary wave front can be considered to be a new source of a secondary spherical wave, and that a secondary wave front can be constructed as the envelope of these secondary waves. So, what he says that when a wave propagates, so every point on that propagated wave that behaves as a secondary wave front, secondary source, and that you can consider that is radiating. So, effectively all these secondary sources, their radiation is same as the main wave front. That was Huygens principle. From that, actually Shelkunov, a very famous electromagnetic theory man, he formulated a principle which is called equivalence principle. In 1930s he made this contribution. Basically there is a theorem called uniqueness theorem by which he found out this equivalence principle. So, what he said is the field in a lossy region is uniquely specified by the sources within the region plus the tangential components of the electric field over the boundary, or the tangential component of the magnetic fields over the boundary, or the former over part of the boundary and the latter over part of the latter over rest of the boundary. So, it is just I have stated it for your knowledge. We will discuss about this. So, it is not that you will have to think. What here he has made a term lossless medium, actually lossy medium. So, lossy medium is nothing but a special case of lossless medium where loss is equal to 0. Actually our free space, actually it is lossy, but we consider it that loss is very small. So, it is can be considered as our usual lossless medium also. So, from equivalence principle we can say that for a source free region, you see Shelkunov has said that you require the knowledge of sources as well as the tangential fields at the surface. Now, if I do not have a source at some region, so for a source free region, we can say that if the tangential electric and magnetic fields are completely known over a closed surface, the fields in the source free region can be determined, and actually by uniqueness theorem there is a guarantee that what we determine, that is the correct solution. So, what is the practical application of this equivalence principle is fields outside an imaginary closed surfaces are obtained by placing over the closed surface suitable electric and magnetic currents densities that satisfy boundary conditions. Now, here there is a thing that for the first time I think in this lecture I am telling about magnetic current densities. Actually, this is again a hypothetical thing. Actually, mankind could separate the electric charges, so we can separate the positive and negative charges. We cannot do that for North Pole and South Pole. So, magnetic poles, they cannot be separated. That is why we cannot have a flow of magnetic poles, flow of north poles or flow of south poles, etc. But in the field wise, we can equivalently say that if there is an electric current density which is flow of charges, so equivalently there will be also magnetic current densities, and we will see just after this how to analytically make that assumption. So, that because if we make this thing in the Maxwell's equation, then the whole Maxwell's equation becomes symmetrical. That we will see that Maxwell's equation suffer from one thing. Suppose if you look at just Maxwell's equation, I have del dot D, divergence of the electric flux density, that is rho, but del dot B, that is 0. So, you see that there is a thing, but if we have separate magnetic charges, I can put this to be rho m. Similarly, what is del cross E and what is del cross H? You can see that in del cross H, I have a J and there is something else, but here you see that in del cross E, I do not have this counterpart of G. So, here if we put a now if I call this J E and if I call this J M, then these two also becomes symmetrical. So, that is the idea, and finally, we will see that what is their actual expression. So, this whole thing gets very symmetric, and that is why in electromagnetics we always assume this, that there is a magnetic current also, and this satisfies the introduction of this, does not change the Maxwell's equation solutions. So, also before going to this actual discussion of this equivalence principle, I will say what is the closed surface. A closed surface means for this equivalence principle that a surface which encloses the sources and they are taken to coincide with the conducting part of the structure or antenna, because then our actually the thing is our integration domain gets very much reduced if we can include in the surface the conducting boundaries, because in the we know that in conducting zones various field things gets cancelled. Now, let us come to the actual problem is, let us say that I have a surface like this, hypothetical surface. Actually, there are, let us say that there are sources. So, how do we characterize sources? A source, just as we said that in actual life in Maxwell's equation, you see who are the sources. The sources are J E and rho, but we say that why there can be also the J M, which actually we do not call J M, we call M. Actually, this J M is given the name M. So, this generally the conducting current, that generally called J. So, J rho, so M and rho M I can say. Now, already these J and rho are related by continuity equation. So, actually I need not consider this. Similarly, I need not consider this. So, actual sources I can say are for electromagnetics are J and M. So, sources means I can say that there is a electric source, electric type of source to be precise, because actually and this is called magnetic type of source. Generally for magnetic this is not a correct notation. Generally two arrows are placed on a magnetic sources to distinguish it from J, and let the medium constitutive thing is epsilon 1 mu 1. So, these sources has produced fields everywhere, let us say E 1 and H 1, because electromagnetic field they will sources mean these are all time varying sources. So, they are producing E 1 and H 1. So, here also they will be producing E 1 H 1, because this is actually this surface is an arbitrary surface. So, everywhere there will be E 1 H 1s, and here also I write that this is mu 1 epsilon 1. I am not saying about the conductivity, that loss thing we have discussed, that more or less that is we can say that lossless medium type of thing. Okay. Now, to distinguish that this zone, you see that this is a closed surface. Why? Because this is completely enclosing the sources. So, this is hypothetical, I have taken this. So, this and let me name this is the surface S, closed surface S enclosing this volume V 1. So, everywhere there are the same thing, and this outside volume outside of this surface let me call V 2. So, this is my actual problem. Now, my actual intention is to find E 1 H 1. You see, think of an antenna problem, that I do not want to know what sources is producing this field, etc. I just want to find out at a radiated zone what is E 1 H 1. So, now this thing can be, so this J 1 M 1 they are radiating fields. So, here inside this surface also it is producing that field, outside also producing that field, etc. Now, this actual problem I will replace with the help of equivalence problem, field equivalence principle, as this same surface S. I have the volume V 1 and I have this epsilon 1 mu 1. Outside also I have epsilon 1 mu 1, that has not changed anything. Now, this one I am calling V 1, outside I am calling V 2. What I now let me say that this is my, the surface has a outward normal. So, this is my direction of that. Now, I say that this is my equivalent problem. I have written it, where is the black? This is my equivalent problem. Here I say that inside I do not consider any sources. So, this V 1 which was earlier containing sources, now I do not consider any sources, but I satisfies the boundary condition here. So, I put on this imaginary surface two current densities. This is actually equivalent currents, one is Js, another is Ms. What is Gs? It is the tangential component of the discontinuity in the magnetic field and ms is the negative of the tangential component of the discontinuity in the electric field. What is there? I will have to show that actually still previous case this outside field was E1 H1, now also outside field is E1 H1. And obviously, since I have removed this, so the fields these sources which was earlier J1 M1 actual sources, I have represented them with some surface sources Js Ms here. So, they will be radiating inside a different field than the previous one. So, that I am writing E and H, different from E1 H1, but these are taken to be such that they will radiate the same thing in the outside. Outside I am not disturbing, and inside field is getting disturbed. But why this outside is not getting disturbed? Because I have taken the sources so that it becomes the discontinuity that is created by placing these, that is tackled here. So, the boundary condition on the surface is unaltered by this choice, and that is why the outside fields are not getting. So, Js and Ms radiate field inside the surface S that is different from actual, but in the volume V2 they produce the correct fields E1 H1. Now, this is the equivalence principles fallout, that I can do this, and then if I am interested only about this, I can go on doing this. So, please understand that this is the equivalent problem, and you see that if we do not take Ms, we cannot get, because in the, if you look at the boundary condition of the electromagnetic field that we have learned in our EM theory days, that there can be discontinuity in the tangential component of magnetic field, there can be discontinuity in the electric field also, as happens suppose in a horn antenna. Suppose in a horn antenna there is no discontinuity in the magnetic field, but there is a discontinuity in the electric field. Now, that we were taking Fourier transform and all this, but aperture there is some, think of the open ended waveguide or horn antenna, that there is an aperture. So, there is certain field was going, suddenly the electric field is getting changed. So, that discontinuity we will have to take, and that is why this introduction of magnetic current. So, magnetic current, it is hypothetical, we are not saying there is a flow, but discontinuity we are calling tangential component discontinuity of the electric field, that we are calling magnetic current, and tangential component discontinuity in the magnetic field, that we are calling. So, I think I got confused, that magnetic field discontinuity in the tangential component of the magnetic field is electric current, and the discontinuity in the tangential component of the electric field is magnetic current. So, both should be present, because in some cases this may be present, in some cases this may be present, or in a generalized case both can be present. So, sources should be of these two type, because you see we generally consider in the electromagnetic cases that if you have a discontinuity in the tangential component of the magnetic field, there should be a surface current which is also tangential electric current, but it is in another direction orthogonal to the n direction. So, that is here. So, similar thing should be here, and that correct thing is here. Please remember that there is a sign change here. These are all for Maxwell's equation, anything. Now, this is equivalence principle fallout. So, now I need not consider this. So, over the surface if I put based on the actual problem, then I can find out, because if I can find out, already we have seen for wire antennas that if I know this current on the wire is nothing but current on that surface. So, from there we have seen we will go to potential and then we will find out the field. Similar way we will show that for MS also this is the current you can find out. We will from Maxwell's equation we will prove that this you can do. So, if there are two present, it will be sum of the field due to J's, sum plus sum of these superposition holds. If only one, this is a classical wire antenna where MS is not 0. The other thing is this is J's is 0 in case of a classical aperture antenna, in general everything. Now, there are some engineering shortcuts to these problems, that you see this E and H can be any field. So, without loss of generality, we can say E H can be 0 also. So, if I take E H 0, then actually Loeb, one scientist, he proposed it, that is why it is called Loeb's equivalent. So, let me draw that E and H, these fields if we take to be 0. So, this is my V1. So, I say fields are now 0 0, these are same epsilon 1 mu 1 etc. So, this is my S, and so this is my N outward, this is my V2. In V2 the fields are same E1, H1, and I have a Js is equal to N cross H1, and I have Ms equal to minus N cross E1. So, you see the surface current densities Js and Ms radiate in an unbounded medium epsilon and omega, epsilon 1 omega 1 mu 1. So, our formulas for EH that we derived for wire antennas can be used here, but this requires knowledge of both E1 and H1 in tangential component over S. So, you see that in wire antennas we have had the knowledge of only J's, but here we require both this knowledge, that means E field and H field both. And now, to simplify this, you see that if we now put, so let me write, this is called Loeb's equivalent. Now, to simplify, you see that problem, that why I will deal with the two things. Let me put that same surface S, but now this is totally I put a perfect electric conductor PEC. I think you know PEC, inside that the fields are 0. So, already here the fields were 0, but I have put a PEC here. I have, this is my V2 and this is my E1 H1. So, PEC I said 0 0. So, now there will be, I will have to put over this surface, and Ms is equal to minus N cross E1 and a Js is equal to N cross H1. So, what is the difference between these? We will show that will show something, but now you see that point is we cannot use the same formulas as we were having in case of unbounded medium. That means, up to here, okay, those if only J is present, I can use the formulas I developed, but this case and this case is different, because this case was just a Js and Ms present, they are radiating in an unbounded medium, not this is bounded, that is bounded. But now this is radiating and back there is a PEC. So, this is not the same problem. So, this is a in presence of PEC how they are radiating. So, that is a different problem, but I will now say that in this case this Js value becomes 0. Why? That means, it says that no field gets radiated by an electric current impressed along the surface of a PEC. How? So, what you do to understand this, understand that I have this sorry, I should have used this color. You have a PEC. Suppose I have a port here, let me call it A, and at a distant point I have another port B. Visualize a set of port or terminals A on this PEC conductor and another set in B in space a bit away from the conductor. Now, if I have a current element here at B, then it produce what tangential electric field it will produce here, since it is a PEC it will be 0. So, I can say that even if there is a current element here, this voltage is 0, because no fields here. Now, I invoke reciprocity. Now, I invoke reciprocity. So, if I have a current element here, what will be the field here? That is 0. So, VBA is also 0. Now, terminal B is arbitrary, it can be taken anywhere. So, I can say that current element on or any conduction current on a PEC does not produce anywhere any field. So, that is why I can put that Js is 0. Now, so that means we have only Ms present here. So, Ms, but the problem is it is having a PEC. So, now we can invoke image theory. So, I can say that if this surface is an infinite plane, this surface is an infinite plane, and in front of that I have an Ms. So, image theory will give me that I do not have a PEC, I have sorry, I should write Ms. So, I have Ms, I do not have anything, I have the original Ms like this. So, this is the image. So, this equivalently I will have 2 Ms radiating in unbounded space. So, I can use the formulas. So, that means this is done. Actually, you see that an open ended waveguide, if we think that the waveguide, the antenna, always we make a ground plane along the open ended waveguide. If we assume that that ground plane is infinite, how you assume? Though in practice we have something, if you take generally 5 lambda sort of thing for a conductor, that ground plane length in all the directions, then you can say that it is an infinite ground plane. So, ultimately you find the current. So, this is a magnetic current. How that magnetic current comes? It is at minus n cross E1. So, twice of that, now that is radiating. So, you can easily find this formula. So, you can find the field. Actually, we will show, if time permits, that the aperture Fourier field thing, etc., instead this also gives you the same result. Similarly, we can also put, instead of PEC, a perfect magnetic conductor. So, if we do that, this is our surface S, the inside is V1. So, the fields are 0, 0, and this whole thing is this is a PMC behind that surface S, and the outside V2, there the original fields E1, H1 exist. So, for equivalence, what we will have to put? We will have to put a JS here and then MS here. Now, this JS will be nothing but n cross H1, and this MS will be minus n cross E1. So, just same as PEC analogy, that if I have an MS in front of a PMC, actually it will be 0. The same way you can consider another point here and then invoking reciprocity, this can be proved. So, I do not have an MS. So, I have simply a JS. So, now this JS radiates in presence of an PMC. So, that is difficult to evaluate. So, what we can do, again like PEC, we can invoke the image theory. So, let us consider that this surface S is an infinite plane. So, we can take that, basically the problem is like this. I have an infinite PMC case, this is S, and in front of that I have a JS, tangential JS. So, by invoking image theory, I can write that equivalent to this is basically this JS, and the image of that will be another JS. So, basically I can say that I have nothing but a 2 JS and the medium is unbounded. So, 2 GS is radiating into an unbounded space. So, this expression we know already. If I have a current density, electric current density in an unbounded homogeneous medium, how it radiates. So, we can easily find the field from here. So, this is the from Love's equivalence principle, you can get these two cases where it becomes easier. Only we will have to have either this JS in PMC case or MS in case of PEC. Okay. Now, if this S is not an infinite plane, but its curvature is much smaller than the lambda, then we can have this same, we can infinite plane approximation holds. Depending on what out of this, whether Love's equivalent we will use or any other equivalent we will use, or PMC, PEC, etc., we will proceed and do that. So, Based on that, we will now discuss that the thing. It will be very simplified, but one thing we will have to proceed, because this is today we introduce the concept of magnetic current. So, we do not know if a magnetic current is present in an unbounded medium, how fields radiate. So, we will have to go to the Maxwell's equation, and first we will derive that if an magnetic surface current is present on a surface, how the fields, what is the expression of the electric field and magnetic field. Then we will make the far field approximation and go to the actual cases. Okay. Thank you.